Okay, I'm gonna get started. First of all, integration problems. So I think I had assigned this problem set on integration. I posted the solutions. They're all there. There were 20 questions. One of them was a repeat, so really there was only 19 questions. I've since then posted 4 more questions that I want you to work on. The answers are there. I didn't post the solutions, but I want you to work on these 4 problems as well, and you can check the answers, and if you have issues with them, we can take those up next class. Are there any issues with understanding the solution to these 20 integrals here that you want me to go over or explain in more detail? Okay, so for more practice then, please actually work on these 6 questions. There's 6 of them there. 21 through 26. The answers are posted, but there's no solutions. See if you can get the answers before I post the solutions. The other thing I want to mention is, some of you may have discovered already, but there is these type of integral calculators online that'll help you. They're free. This one here is free. There's the link for it. When you type in the function, it'll actually show you the steps involved, so that may be helpful for you in when you're working through these things, but it's not 100% necessary. I just thought I'd point it out to you. That brings us to area approximation methods. We started this last class, and we talked about how do I approximate area under a graph, and there were three approximation methods that we talked about. A left rectangular approximation method, which uses the left height of each rectangle, so the top left corner of the rectangle lines up on the function. We talked about a right rectangular approximation where the top right hand corner of the rectangle lines up on the function, and we talked about midpoint. And I don't exactly remember where we left off. Did we get through this entire example? Did I start this example? So this is page 10. I don't remember where we left off. Anybody? Nobody wants to help?
I think we did it, sir.
Yeah, I think we already did it.
We did the whole thing?
Yeah, I think we're on the next one.
This chart right here?
Yeah, we talked about this.
Okay, also, we didn't start trapezoids though, did we?
No,
We
I don't
did.
think so.
Okay, so let me I'll start with this slide here and I'll go from there. So this slide here, this chart, all this is doing is summarizing LRAM and RRAM. When would you get an underestimate and when would you get an overestimate? So if the function is increasing, the top half of this chart shows that if the function is increasing, and it doesn't matter whether the function is concave up or concave down, as long as it's increasing, LRAM would give you an underestimate, and the right rectangular approximation would give you an overestimate. When the function is decreasing, which is the lower half of the chart, no matter whether the decreasing function is concave up or concave down, that doesn't matter. As long as the function is decreasing, LRAM will give you an overestimate of the area, and RRAM will give you an underestimate of the area. And that's all that chart's meant to do, is just to summarize that. So given that we've covered those three methods, the next method is using trapezoids. So we're not going to be using rectangles. We're going to be using trapezoids to approximate the area. And using trapezoids is more accurate than using rectangles. So if you're using, let's say, LRAM with 5 rectangles or RRAM with 5 rectangles, neither one of them will be as accurate as a trapezoidal approximation with 5 trapezoids. So as long as you're comparing the same number of either rectangles or trapezoids, the trapezoid approximation will be more accurate. So you can see there on this slide, I'm approximating the area under that black curve there, and the shaded trapezoids are purple, and there are 3 of them. Okay, so you can see what the shape of a trapezoid looks like. So what we're going to do now, because we have trapezoids, we're going to add up the areas of the individual trapezoids instead of adding up areas of rectangles. Before we can do that, we need to understand or know how to find the area of a trapezoid. So all our trapezoids are going to have this basic shape here that I've shown below, that I've colored in yellow. Okay, that's the basic shape all our trapezoids will have. On the left-hand side, it will have a height. And from the diagram, you can see on the right-hand side, the height is a little bit higher. Sometimes it'll be the opposite way, but the point is that on the left-hand side and right-hand side, you'll have 2 different heights. And this trapezoid will have a width. And in the diagram there, I've given the width the name delta x. So the width of that trapezoid is delta x. The area of each trapezoid is just the average of those 2 heights. So I add the 2 heights and divide by 2. And then I just multiply by the width. That is the formula for the area of each individual trapezoid. So you just do that calculation for every single trapezoid, and then you add them up, and you'll have an approximation for the area. So some examples. And I've already put the solution in here because I've gone through this with the other class. Given the function f of x equals x squared plus 1, which is graphed there in the picture, that is the graph of x squared plus 1, approximate the area under that graph from x equals 0 to 2 using a trapezoidal approximation with 4 equal subintervals. So it's telling you to use 4 trapezoids with equal width. 4 equal subintervals means 4 equal width trapezoids. So the width of each trapezoid would be a half, right? You take 2, subtract 0, and divide by the number of trapezoids you're using. Okay, and you'll get a width of a half, which is I've written under the graph there. Now, we're going to add up the area of trapezoid 1, trapezoid 2, trapezoid 3, and trapezoid 4. Since the width of every trapezoid is exactly the same, and that width is 0.5, I've factored 0.5 or 1/2 out of that large rectangular or square bracket. So that is the width of each trapezoid. Now, I have to multiply the width of each trapezoid by the average of the two heights of each trapezoid. So for T1, that would be, the left-hand height would be f at 0, and the right-hand height would be f at 0.5. So to average those heights, I just divide by 2. And that gives you the first expression in the square brackets. Then I'm going to add to that the average of the two heights of trapezoid 2. And then I'm going to add to that the average of the two heights of trapezoid 3. So for that one, it would be f at 1 plus f at 1.5. Okay, divide that by 2 because you're finding the average. And then the average of the two heights of trapezoid 4, which would be f at 1.5 plus f at 2.0 divided by 2 because we're finding an average. And you take each one of those and you're going to multiply by 1/2, but I factored the 1/2 outside the bracket. Now you can see that I've highlighted, you can see that f at 0.5 shows up twice. F at 1.0 shows up twice in the square bracket. F at 1.5 shows up twice. But the left-hand height of the first trapezoid, which is f at 0, only shows up once. And the right-hand height of trapezoid 4, the last trapezoid, only shows up once. That's f at 2.0. So if you look closely enough at that expression, you can rewrite it the way that I did there. You can see that there's a 1/2 in each term. So in addition to having the 0.5 outside, you can factor out 1/2. And you would have 0.5 divided by 2 on the outside of the bracket. And then all you're left with on the inside is f at 0 plus 2 times f at 0.5 plus 2 times f at 1.0 plus 2 times f at 1.5 plus f at the last x value, which is 2.0. That'll always happen. That kind of pattern will always happen when you're using a trapezoidal approximation. So sometimes it's easier just to skip right to that last step, if you can remember it. Now, you're left with subbing 0.5, 1.0, and 1.5, and 2.0. You have to evaluate f, the function, at those values. And when you do that, you get a 4.75 as your approximation for the area. That's how a trapezoidal approximation works. Are there any questions on that? So it's important that you understand how that calculation works. And you're even better off if you can go right to that last line. It'll work like that every time. Okay? Now, part B. We want to compare the trapezoidal approximation with the left and right hand rectangular approximation, because there's an interesting relationship between the two. Okay? And it'll always hold true. So using a left rectangular approximation, okay, so now we're using rectangles for part B. The width of each rectangle would be 1/2. And if we're using LRAM, the left-hand side of each rectangle, the top left corner, forms the height of the rectangle. So that would be f at 0 plus f at 0.5 plus f at 1 plus f at 1.5. Plug those numbers into the function, which is x squared plus 1, and you get that the left rectangular approximation is 3.75. Do the exact same thing for RRAM, except now you're using the right-hand side of each rectangle. the top right corner has to line up on the function. So that would be f at 0.5 plus f at 1 plus f at 1.5 plus f at 2. 0.5 is the width of every rectangle, so we multiply each of those by 0.5 and we get 5.75. So now I want to compare the trapezoidal approximation, which is 4.75, with the LRAM and RRAM, and you can see that you can come up with this relationship that the trapezoidal approximation is just the average of LRAM and RRAM. So all you got to do is take LRAM, take RRAM, divide by 2, and that'll give you the trapezoidal approximation every time, as long as you're using the same number of intervals. Okay, that's important. So in part A we used 4 trapezoids, and in part B we used 4 rectangles. It's only when you're using the same number of rectangles and trapezoids that that relationship is true. It makes no sense to say that the trapezoidal approximation with 10 rectangles, with 10 trapezoids, would be the same as the average of LRAM and RRAM with a different number of rectangles. Okay, so you have to use the same number of rectangles as trapezoids, and when you do, that relationship is true. The trapezoid approximation is just the average of LRAM and RRAM. And so I've highlighted that. For same number of subintervals, that's the important part. So why is that helpful? It's helpful because on an exam, or on the AP exam, you may be given a question where they say, find the trapezoidal approximation, and there may be 5 trapezoids, it may be 6, 7, or 8 trapezoids. I think you would agree that it's easier just to find LRAM and RRAM and divide those answers by 2, just find the average of them, than it is to do the trapezoidal approximation. Look at the calculation in A, and then look at the calculation in B, and I think you would agree that if you just found LRAM and RRAM and then found the average, that would be easier than all that nonsense in part A. So that's the whole point of showing you that relationship. Any questions on that? Okay, page 14 is just more examples. So now we've got the function 9 minus x squared, and you want to approximate the area from 0 to 3 using a trapezoid but with 6 subintervals. Okay, so that means 6 trapezoids. Now I didn't draw the trapezoids in there, obviously, because then the diagram is going to become ugly. But I've labeled, so I've taken 3.0 and divided by 6. Our width is going to be a half. Okay, so you can see the partition, the x values, I've split up 0.5, 1.0, 1.5, 2.0, 2.5, 3.0. You can see all that on the graph. The expression for the trapezoidal approximation, you can see it there, is quite involved. So it's for every trapezoid, you take the width and you multiply it by the average of the heights. So you can see that there's 6 expressions there, 1 for each trapezoid. But then again, just like the last problem, you notice that each one of those is divided by 2. So I can take out the 1/2 outside and then just write f at 0 plus 2 times f at 0.5, f at 1, f at 1.5, f at 2.0, and f at 2.5, plus f at 3. So it's the first and last ones, there's only one of them, but everything in between, there's 2 of them. That'll always happen. with the trapezoidal approximation. So all that's left to do is plug those values into the function, and I got 17.875. Now, if we had done the LRAM and RRAM, it probably would have been simpler. And then all I would have had to have done is take the average of them, add them together and divide by 2, and I would get the exact same number, 17.875. But I would have to use 6 rectangles. I didn't do it there because I just wanted to show you. I think we've done enough of the LRAM and RRAM, but that would be the calculation for the trapezoid if you did it that way. The next example is the same idea. It's asking for a trapezoidal approximation of a function that's given to you in a table rather than an equation or a graph. Now you can see from the table that the x values are all the same distance apart. They're all 0.5 apart. And so that would give you 6 trapezoids. That's a uniform partition. 6 trapezoids. So you're going to add up the area of the 6 trapezoids. And I've written the area out there. It's 0.5 times the average of the heights of each trapezoid. So for the first trapezoid, it would be 2 plus 4 divided by 2. Multiply that by a half. For the second trapezoid, it would be 4 plus 6 divided by 2. 4 and 6 are the 2 heights. Divide that by 2 and multiply by the width of a half. The third trapezoid, you would be using 6 and 7 as the heights. Add those together, divide by 2, multiply by a half. And you go all the way through the table till you get to the end. 1 and 5, those are the two heights of the last trapezoid. So add 1 and 5 divided by 2 and multiply by a half. And then it's just fairly straightforward math. And you should get 12.75 as the area, the approximation of the area. Questions? Any questions? Nothing? Okay, so 4 methods: LRAM, RRAM, the midpoint. Those 3 are all rectangular approximations. And the fourth one is a trapezoid. The trapezoid involves a little bit more math, so it's a bit lengthier than the other 3. And the relationship between the trapezoid and the 2 rectangular LRAM and RRAMs is that for the same number of subintervals, the trapezoid is the average of LRAM and RRAM. And we can use all 4 of these methods to approximate the area under a curve, given to you as a graph, given to you as a function, or given to you as a table. That is what we've done here in this lesson. Any questions before I move on? Okay, so that brings us to part 2 of this approximation methods. Now, big picture, we're still going to be approximating areas under curves, but this time we're going to be interpreting those areas. In other words, these are real-world problems where you might have to find the area under a curve, and it'll give you a useful bit of information. So, example 1, the following graph represents the speed in meters per second of a vehicle traveling in a straight line for 10 seconds. So this is you driving down the highway, at 10 meters per second for 10 seconds. You can draw, the graph is just a straight line at 10 meters per second, and that goes from 0 to 10. What's important for you to note now is that speed, the graph here, represents a rate of change. When you hear those words, rate of change, you should be thinking derivative. A derivative is a rate of change. And it's important when you are dealing with rate of change that you take note of the units that are involved. So meters per second. And now we're going to find in this example and the ones that follow, we're going to find the area under a rate of change function. And what does that mean when we do that? So this is a rectangle. It's simple to find. We don't need any trapezoids or any other kind of fancy method to find that yellow highlighted area. It's just a rectangle. So it's 10 meters per second. That would be our height. This is a height. And this is just the width. And when you multiply 10 by 10, you get 100. But what's important to note is that the seconds cancel each other out. Okay, so the 10 meter per second speed multiplied by 10 seconds gives us an answer of 100 meters. So that area is 100 meters. That would indicate, those units would indicate that the area represents the total distance traveled over those 10 seconds. Which makes sense, right? If you're traveling at 10 meters per second for 10 seconds, you just multiply the speed by the time and you'll get the distance, 100 meters. Okay? So the total distance traveled over the 10 seconds is 100 meters. Let's move on to the next example. Again, we have a rate of change graph, which is a derivative graph. Derivative of what? Well, in this example, we have a rate measured in liters per hour. It's the rate at which the methane gas is being produced in a cave over a 12-hour period. And that function can be modeled by the equation given there, 0.125x squared plus 1. So that curve is a rate. The units are liters per hour, which represents volume. Liters is volume, hour is time. So we have a rate of volume changing with time. So, part A says, approximate the area under the graph using LRAM with 6 subintervals. So we're going to use rectangles. We're going to find the area of these 6 rectangles and add them up. Now, on the left-hand side of the graph, what I've written is that the height of each rectangle, the units would be liters per hour. And the width of each rectangle has the units of hours. So when you multiply the height of each rectangle by the width, you're going to get a unit of liters. And liters would tell you that the area then that you're finding is going to represent the volume. Okay? So when we add up the areas of all 6 rectangles, it's going to give us the volume of methane that was produced in the cave. So if we step back a second and look at what we're given a rate graph, a derivative graph. What is our derivative function? It's volume changing with time. when you find the area under that rate function, when you find the area under that derivative function, it represents the volume, which is the quantity changing in the rate. Volume per unit time is our rate. Find the area under that graph, it gives you the total volume. So I've done the calculation there. The width is just 12 minus 0 divided by 6. So each rectangle has a width of 2. Okay. So for LRAM, it would be 2 times f at 0 plus f at 2 plus f at 4 plus f at 6, f at 8, and f at 10. I sub those numbers into the function, and I get that the area, when I add up the areas of those rectangles, I get 67 liters. So what that means is the area under the graph represents a volume. It's the volume of methane produced in the cave over the 12-hour period. Any questions on that? So keep in mind that these rates here, when we're finding the area under a rate curve, it's the same as finding the area under a derivative curve, and it represents the total change in the quantity that's changing. So in this case, we had volume changing with time, so the area would represent the volume. All right, next example. Same idea again. The following graph represents the rate in liters per minute at which the volume of water in a tank is changing over a 6-minute period. And the function that models that curve is, there's a negative sign missing, which I've added there. It's actually negative 0.5 x minus 2 squared times x minus 6. That curve is a derivative graph. It's the volume changing with time. Okay? So it's a rate. We're going to use a trapezoidal approximation in part A with 6 subintervals. And you can see I've drawn them there in red. There are 1, 2, 3, 4, 5, 6 trapezoids. The width of each trapezoid is 1. Okay, so I've gone to the shortcut method for this trapezoid. In other words, I've gone right to the last step. The 1.0, which is the W, I've written outside the square brackets. So this number here, 1.0, is the W. W divided by 2. Okay, so I've taken the factor of 1/2 outside the brackets, and I'm just adding up f at 0, 2 times all the ones that are in between, and then f at 6, which is the last one. If you go back and look at the trapezoidal approximations, those examples I did, I just skipped right to the last step to save some time. It's always going to be the same. It's going to be W divided by 2 multiplied by f at 0, and then 2 times all the ones in between, and then f at the last point, which is f at 6. Okay. If I sub all those values into that function, of course I use the calculator here, I got 18.5 liters. So again, for each trapezoid, I'm multiplying a height, well, the average of the two heights. So I take one height, the left-hand height, the right-hand height, divide by 2. The units of that would be liters per minute. And then I'm multiplying by the width of the trapezoid, which is in minutes. And I see that the minutes cancel, and I'm left with units of liters. So the area of each trapezoid represents a volume again. So what is the interpretation? What does it represent? Well, what it means is that 18.5 liters of water have been added to this tank over the 6-minute interval. So how do I know it's been added and not subtracted? The reason is because all our trapezoids are above the time axis. In other words, all the rates are positive. Every part of this graph is above, so all the water has been added to the tank over the 6-minute period. Any questions? Okay, next example. A little bit different. Okay, this time we have a rectangular swimming pool. 30 feet by 50 feet. 30 feet wide, 50 feet long. And the table here shows how deep the water is at 5-foot intervals, starting at one end at x equals 0. And then at every 5 feet, you're given the depth until you reach the other end, which is 50 feet, right? Because this pool is 50 feet long. So on the left-hand side of the table, you can see that what I've done there. I'm kind of drawing a profile or a cross-sectional view of the swimming pool from 0 to 50. So at 0, it's got a depth of 6 feet. Then at 5, if I move over 5 feet, the depth is 8.2 feet. I move over another 5 feet, the depth is 9.1, and then 9.9, and then 10.5. And I can continue like that all the way over to 50. So we're being asked to estimate the volume of water in the pool given those dimensions. So if we look at, so for part A, we're asked to use LRAM. So basically what I'm doing here is I'm taking that cross-sectional profile and I'm gonna approximate, I'm gonna use rectangles. Okay, the width of each rectangle obviously is 5. Okay, so let me just do this. So for LRAM, that would be my first rectangle. Second, third, fourth, and I'm just going to sum up all those rectangles. So it's going to be 5, which is the common width, multiplied by, if I'm using LRAM, 6 plus 8.2 plus 9.1 plus 9.9, all the way up to 12.7. That's going to give me the cross-sectional area of the swimming pool, but I have to multiply that by 30 because the width of the pool is 30. So I end up getting 30 times 465.5. Okay, my answer is 13,965, and the units are cubic feet. I can do the exact same thing with RRAM, okay, except this time my rectangles look slightly different. This time they're going to look like this. So I'm kind of doing this, right? So it's going to be 5 times oops, I didn't draw that right. Yeah, I did. 8.2, 9.1, 9.9, 10.5, all the way to the end, 13.0. Multiply that by 5 because the width of each rectangle is 5. And then I need to multiply by 30 because the pool is 30 feet wide. And when you do that, you get 15,015 cubic feet. Now, rather than using rectangles, yes, we could use trapezoid. Okay, there's the calculation for trapezoid. I used the shortcut. Okay, so 6, and then 2 times all the depths in between, except for the last one of 13. multiply that by the W, the width, which is 5, but don't forget for trapezoid we got to divide by 2. And then multiply by the width of the pool, which is 30. And we get 14,490. So I'll let you stare at that for a minute. Are there any questions? This part C here, this was the long way of doing that, okay? Because I already had the left rectangular approximation and I've already had the right rectangular approximation. So I already had this number here and this number here. The trapezoidal approximation, I could have avoided all that math and just taken the average of the LRAM and the RRAM. Okay, so I could have done this. I could have taken 13,965, added 15,015 and divided by 2, and I would get the exact same thing, 14,490 cubic feet. So here's where it would have paid off to know that relationship and use it. I did the trapezoidal, I did all the calculations, but I just want to point out that we could have used the shortcut there for the trapezoid because the number of rectangles in trapezoid is the same. Okay, next example. Oil is leaking out of a tanker that's damaged at sea. And the damage to the tanker is worsening as evidenced by the increased leakage each hour. So you can see that we're being given how fast the oil is leaking out after each hour. So originally it's leaking out at 50 gallons per hour, and you see that number is climbing all the way up to the 8th hour where it's leaking at 720 gallons per hour. Part A says estimate the amount of oil that has escaped in the first 5 hours using LRAM and RRAM. So look at the table and you can see the units is in gallons per hour. So we're finding the rate, we're finding the area under a rate function. We're going to take gallons per hour and multiply it by hours. That's going to give us gallons, which is the volume. So in the first 5 hours, you can see that the width is just 1, right? Whether we're using rectangles or trapezoids, the difference between each time value is just 1. So that's our width. And for LRAM, it would be 50 plus 70 plus 97 plus 136 plus 190 for the first 5 hours. That would give us 543 gallons of oil. Okay, again, this is a rate. The area under a rate graph gives us the quantity of whatever's changing. In this case, it's volume. RRAM, same idea. You would get 758 gallons. Part B says estimate the amount of oil that has escaped over the entire 8-hour period using a trapezoidal approximation. So rather than doing the trapezoidal approximation, this time what I did was I found LRAM, I found RRAM, and then I just found the average. And I think that that is a lot easier than actually finding the area of all 8 trapezoids and adding them up. This is much quicker. I just take my LRAM approximation and add the RRAM approximation and divide by 2. And that will give me the amount of oil that has escaped over the 8-hour period. So again, we have volume changing with time here. And if we find the area under volume changing with time, that will give us the change in volume. In other words, the number of gallons or the amount of oil that has escaped. Any questions? Okay, is this the last example? Yeah. So last example here is slightly different. So now we've got a rate graph, again, liters per minute again, but this time part of it is above the time axis and part of it is below the time axis. And I've shaded the part above in yellow and below in green. Okay, so we're going to find the area under this rate graph. In part A, it says approximate the area using RRAM with 8 subintervals. And what does the area represent? Just from 0 to 8. So this is the yellow, the yellow part. So the width is 1. And keep in mind again that your rectangles over here, this is your height, and you're multiplying by a width, and your units are liters again. We've got a rate of volume per unit time, and when we find the area under that, it will give us the change in volume. So, width of 1 multiplied by, if I'm using RRAM, that would be, and I'm just reading the values off the graph, right? So I would be like 35 is here, and here, and here, and you can just read those off the graph. So 35 plus 30 plus 25 plus 20, all the way down to 0. That gives me 140 liters, which means 140 liters of water have been added to the tank. Then in part B, it says approximate the area under the graph. What that means is between the graph and the x-axis, using RRAM with 8 subintervals. What does this area represent? So that would be a width of 1, and if I'm using RRAM, it would be here, which is 5, 10, 15, 20, 15 again, 10, 5, and 0. Now, some of you may be asking me, why didn't I put -5 and -10 and -15? So the reason is because we're finding areas. Areas of shapes. Areas are not negative. It makes no sense to say that the area of a trapezoid is -10 or the area of a rectangle is -20. So we're just using those lengths. Okay, the absolute value. So it's 10 and 15 and 20. So when I add those up and multiply by 1, I get 80 liters. Now, the interpretation is that because that is below the time axis, that water is actually being removed from the tank from the time t equals 8 to t equals 16. So, over the first 8 minutes? Over the first 8 minutes, I'm adding water, and over the last 8 minutes, I'm subtracting water. So, part C, what is the net change in volume of water in the tank? Well, if we've added 140 liters, and then we've removed 80 liters, the net change is 60 liters. Okay? That's going to become important later on. You're going to be answering several questions like this, and in the future, what we're going to do is we're going to tie this into integrals. Okay, what is the relationship here between this and integrals? That's what's coming soon. So the net change over the 16-minute interval is 60 liters. Are there any questions on that? Okay, so just to summarize, you can think of summing the areas of rectangles, or trapezoids for that matter. As you add up the rectangles or add up the trapezoids, you are accumulating area. You're adding areas as you move along. The more rectangles you have, or the more trapezoids you have, the more area you're accumulating. Okay? The accumulation of the area under a rate of change of some quantity, we used volume quite a bit today, but the accumulation of area gives the accumulation of that quantity. So what I'm saying is, if you find the area under a volume per unit time multiplied by time graph, that will give you the net change in volume. If you find the area under a velocity time graph, that will give you the net change in position. Okay, velocity is just the rate of change of position. If you have the area under the rate of change of some quantity Q versus time, that will give you the net change in that quantity Q. And that's it. So the area under a derivative or a rate of change graph tells us how much the quantity has changed. It gives us the net change in that quantity. And that's it, folks. Any questions? Okay, so the only thing I've got for you to do then is to please go back and work on these 6 integrals. The answers are there, and if you have any questions, we'll take them up next class. That's it. Have a good day, unless you have questions.
Thanks, sir.
Okay, have a good
day.
one.
Thank you, sir.
See you, sir. Have a good one.
Thanks.
Thank you, sir.
Have a good
Bye,
day.
sir.